Right. Back again for another deep dive. This time, we're going to be looking at something pretty fundamental to chemistry. It's all about how atoms join up with each other, something we call bonding.
Bonding, yeah.
Now, we covered a lot of ground in our last deep dive on atomic structure, so if you haven't checked that out yet, I highly recommend giving it a listen. But in a nutshell, atoms, the building blocks of everything around us, well, they're not just these tiny little balls bouncing around on their own, are they? They're interacting with each other, forming connections. And those connections ultimately determine what a substance is like, whether it's a solid, a liquid, or a gas at room temperature, how strong it is, whether it conducts electricity, all sorts of things.
Yeah, absolutely. It's amazing how the way those tiny atoms connect up can have such a huge impact on the properties of materials.
Exactly. And that's precisely what we're going to unpack today. We'll be exploring the three main types of strong chemical bonds. Yeah. Ionic, covalent, and metallic, looking at how they work, the kinds of structures they form, and ultimately how those structures explain the properties we observe in everyday materials.
Right. So let's kick things off with ionic bonding.
Sounds good. Now, ionic bonding is what happens when a metal, let's say sodium, meets a non-metal, like chlorine. What's the deal here? What's going on between them at the atomic level?
So imagine this. Sodium, being a metal, particularly one in group 1 of the periodic table, it's got this one lone electron in its outer shell. It really wants to get rid of that electron to achieve a stable, full outer shell, just like the noble gases.
Right. Those noble gases, they're pretty content with their full outer shells, aren't they? They don't really react with much.
Exactly. So sodium's looking to offload this electron. Now, along comes chlorine, a non-metal from group 7, and it's only got 7 electrons in its outer shell. It's just one shy of a full set, a full octet. It's desperate to get that extra electron to become stable.
So it's a match made in heaven, really. Sodium wants to lose an electron, chlorine wants to gain one. What happens next?
Well, sodium basically donates its electron to chlorine. This transfer of electrons changes the charge of each atom. Sodium loses a negative electron, so it becomes a positively charged ion, written as Na plus S. Chlorine gains that negative electron, so it becomes a negatively charged ion, ClL.
Okay, so we've got these oppositely charged ions.
Yeah.
Now, we know that opposites attract, right? So what happens to our sodium and chloride ions?
They're drawn to each other like tiny little magnets, and they arrange themselves in a very specific, highly ordered, three-dimensional structure called a giant ionic lattice. Each positive sodium ion is surrounded by negative chloride ions, and vice versa.
So it's not just a random jumble of ions, it's this incredibly organized structure. And what's holding them together in this lattice?
Strong electrostatic forces. That's just the fancy way of saying the attraction between opposite charges. These forces act in all directions throughout the entire lattice, making ionic compounds very strong and stable.
Right, so we've got these really strong forces holding everything together.
Yeah.
What impact does this have on the properties of ionic compounds? Like, let's take our table salt, sodium chloride as an example.
Okay, think about this. To melt a solid, you need to supply enough energy to overcome the forces holding the particles together, allowing them to move freely. And because those electrostatic forces in ionic compounds are so strong, it takes a lot of energy to pull those ions apart.
So that explains why ionic compounds like salt tend to have really high melting points.
Exactly. And the same goes for boiling points, which are even higher. It takes a lot of energy to completely separate those ions into a gas.
Okay, that makes sense. What about electricity? We know if you put a wire across a lump of salt, it doesn't conduct electricity. But if you melt it or dissolve it in water, it does. Why is that?
That's a great question. When an ionic compound is in solid form, those ions are locked in place within the lattice structure. They can vibrate a bit, but they can't really move around freely. And for a material to conduct electricity, you need charged particles that are free to move and carry the charge.
So in a solid ionic compound, those charges are essentially stuck, like cars in a traffic jam, unable to move along and carry the current.
Exactly. But when you melt the compound or dissolve it in water, those ions break free from the lattice and become mobile. Now they can flow and carry an electrical current, just like those cars finally able to move on an open road.
Makes perfect sense. Right, so that's ionic bonding in a nutshell. Now let's move on to covalent bonding. This is quite different, isn't it? It's not about transferring electrons, is it?
Right. Covalent bonding is all about sharing. Instead of one atom completely giving up an electron to another, atoms involved in covalent bonding share pairs of electrons. Think of it as a compromise. Each atom contributes an electron to a shared pool, And by doing so, they both effectively achieve a full outer shell.
Like two kids sharing toys, so they both get to play. And this type of bonding usually happens between nonmetallic elements,
You
right?
got it. Like hydrogen with oxygen to form water, or carbon with hydrogen to form methane, the main component of natural gas.
Okay, so covalent bonding leads to the formation of molecules. What can you tell us about the structures and properties of substances made up of small molecules, like water?
Well, the covalent bonds holding the atoms together within each molecule are very strong. But the forces between those individual molecules, what we call intermolecular forces, are much weaker.
So it's like those atoms within a molecule are superglued together, but the individual molecules are only held near each other with weak sticky notes.
Yeah, that's a good analogy. Now, because those intermolecular forces are relatively weak, it doesn't take a lot of energy to overcome them. This means substances made of small molecules tend to have low melting and boiling points. Think about water. It boils at 100 degrees Celsius, which is relatively low. You don't need to break the strong covalent bonds within the water molecules to boil it, just those weaker forces between them.
Okay, that makes sense. And what about conductivity? Do small molecules typically conduct electricity?
Generally, no, because they don't have any overall electrical charge, and there aren't any free electrons or ions floating around that are able to carry a current.
So those charges are pretty much stuck within each molecule, unable to flow through the material. You mentioned something interesting earlier about the size of the molecules influencing those intermolecular forces. How does that work?
Right, so as those small molecules get bigger and have more electrons, the intermolecular forces between them become stronger. This means that larger small molecules tend to have higher melting and boiling points compared to tiny ones.
Okay, so it's not just about being covalent. It's also about how big the molecules are. That's interesting. Now, covalent bonding isn't just for small molecules, is it? We also have these giant molecules called polymers. What are they like?
So imagine those small molecules we just talked about, like ethene, linking up end to end thousands of times to form these extremely long chains. Each link in the chain is held together by strong covalent bonds, and that's what makes up a polymer.
So it's like a long, long train, with each carriage representing a small molecule, all hooked together with those strong covalent bonds. And what sorts of properties do polymers tend to have?
Well, because those chains are so long, the intermolecular forces between them become quite significant, although still not as strong as in ionic compounds. This means that polymers can be flexible, like the plastics we use every day, but also strong enough to be molded into solid objects.
Right, so polymers are somewhere between small molecules and those giant ionic lattices in terms of how strongly their particles are held together.
Exactly. Now, moving on to a different type of giant structure, we have giant covalent structures, sometimes called macromolecules. These are really on a whole other scale.
Like what, for example?
Think diamond. In a giant covalent structure, you have a vast network of atoms, all linked together by strong covalent bonds. Each carbon atom in diamond is bonded to 4 other carbon atoms, and this tetrahedral arrangement continues throughout the entire structure.
Wow, so it's not just a big molecule. It's one massive, continuous network of atoms, all bonded together. And what does this mean for its properties?
Well, because you have to break an enormous number of those strong covalent bonds to melt or boil it, diamond has an incredibly high melting point, one of the highest of any known substance. It's also incredibly hard, which is why we use it in industrial cutting tools, and doesn't conduct electricity because all those electrons are locked up in those strong bonds.
It's amazing how those tiny little atoms, just by the way they're bonded, can create something as hard and durable as a diamond.
Absolutely. And then on the other end of the spectrum, you have graphite, which is also pure carbon, but incredibly different.
Right. Graphite, the stuff in pencils, soft and slippery. And it can conduct electricity. How is that possible when it's made of the same stuff as diamond?
Well, in graphite, each carbon atom is only bonded to 3 other carbon atoms, forming layers of hexagonal rings, like a honeycomb pattern. These layers are held together by weak intermolecular forces, so they can easily slide over each other, making graphite soft and slippery.
Ah, so it's like those sheets of atoms are able to slip and slide past each other. That makes sense for why it's used in pencils.
Yeah.
As you write, those layers flake off onto the paper.
Exactly. And here's the interesting part about graphite. Each carbon atom has 1 spare electron that isn't involved in those 3 covalent bonds. These electrons are delocalized, meaning they're free to move throughout the layers, just like the electrons in metals.
And that's what makes graphite able to conduct electricity.
Precisely. It's those delocalized electrons flowing through the layers that carry the electrical current. So you have diamond, this incredibly hard, non-conducting material, and graphite, soft, slippery, and a conductor. And they're both made of the same element, carbon, just arranged in different ways. It really highlights how the structure dictates the properties.
It's fascinating. Okay, we've covered ionic and covalent bonding. Let's tackle the third type, metallic bonding. What's going on here? How are metal atoms held together?
So, in a metal, the atoms lose their outer electrons to form positive ions. These ions are arranged in a regular repeating pattern, a bit like a neatly stacked pile of oranges. And surrounding these ions is what we call a sea of delocalized electrons.
Okay, so not a transfer of electrons like in ionic bonding and not sharing between specific atoms like in covalent bonding. It's more like a shared pool of electrons that all the metal ions contribute to.
Exactly. Those delocalized electrons aren't tied to any particular ion. They're free to roam throughout the entire structure. And it's the attraction between those positive ions and that sea of negative electrons that holds the metal together.
So it's like those electrons are the glue that keeps the metal ions from flying apart. And this kind of bonding explains a lot about the properties of metals, doesn't it?
It does. Firstly, because those metallic bonds are strong, metals generally have high melting and boiling points. It takes a lot of energy to overcome those strong attractions.
Okay, that makes sense. And what about conductivity? We know metals are great conductors of electricity. How does that work?
Well, those delocalized electrons are crucial here. Because they're free to move throughout the structure, they can easily carry an electric current. When you apply a voltage across a metal, those electrons flow towards the positive terminal, creating that flow of charge that we call electricity.
So it's like having a highway for those electrons to zip along, carrying the current.
Yeah, that's a good way to think about it. And the same goes for thermal conductivity. Those mobile electrons are also really good at transferring heat energy. If you heat one part of a metal, those electrons gain kinetic energy and quickly spread it throughout the structure, which is why metals heat up so quickly and evenly.
Right, so those delocalized electrons are responsible for both electrical and thermal conductivity in metals. What about their malleability and ductility? You know, how easily you can bend and shape metals or draw them into wires. How does metallic bonding allow for that?
Because those layers of positive ions can slide past each other without breaking the metallic bonds, the delocalized electrons act like a kind of lubricant, allowing those layers to move without the structure falling apart.
So it's not like those ionic lattices where the ions are locked in place. The metallic structure is more flexible.
Precisely. And this property is what makes metals so useful for all sorts of things, from making tools and machinery to constructing buildings and bridges.
Now, what about alloys? We know they're mixtures of metals. How does mixing different metals together affect the properties of the resulting alloy?
Well, when you mix different metal atoms together, you're essentially disrupting that regular ordered arrangement of ions in the pure metal. The atoms of the different metals often have slightly different sizes, so they don't fit together quite as neatly.
It's like throwing a bunch of different sized marbles into that neatly stacked pile of oranges. It's going to make the structure more irregular.
Exactly. And this disruption actually makes the alloy harder and stronger than the pure metals it's made from. The layers of atoms can't slide past each other as easily because they're getting jammed up by those differently sized atoms.
So it's like adding those different sized marbles makes it harder for the layers to move smoothly. And this is why alloys are often used in situations where you need something tougher than a pure metal, right?
Right, like steel, which is an alloy of iron and carbon. It's much stronger than pure iron, which is why it's used in construction, bridges, and all sorts of other applications. Okay, so we've explored the three main types of bonding. Now let's dive into a really fascinating element, carbon. Carbon is amazing because it can form so many different structures, leading to an incredible variety of materials.
Right, like diamond, the hardest natural material we know of, and graphite, which is so soft it's used in pencils.
Hmm.
And they're both made of pure carbon. How is that possible?
The key difference lies in how those carbon atoms are arranged and bonded to each other. In diamond, each carbon atom forms 4 strong covalent bonds with 4 other carbon atoms, creating this incredibly strong, rigid, three-dimensional network. That tetrahedral arrangement of bonds, repeated throughout the entire structure, makes diamond incredibly hard and gives it an extremely high melting point.
Okay, so every carbon atom is essentially locked in place by those 4 strong bonds, making the whole structure incredibly tough.
Exactly. And because all of the outer electrons in each carbon atom are involved in those bonds, there are no free electrons left over to conduct electricity, so diamond is an electrical insulator. Now compare that to graphite. where each carbon atom only forms 3 covalent bonds with other carbon atoms. This forms layers of hexagonal rings, sort of like a honeycomb pattern. Those layers are held together by weak intermolecular forces, so they can easily slide past each other.
Right, so instead of that rigid 3D network you have in diamond, you have these flat layers that can slip and slide. That explains why graphite is soft and slippery enough to use in pencils.
Right, and here's the other key difference. Each carbon atom in graphite has one spare electron that isn't involved in those 3 covalent bonds. These electrons are delocalized, so they're free to move within those layers, just like the electrons in a metal.
Ah, so that's why graphite can conduct electricity. Those free-moving electrons can carry a current through the material. It's amazing how such a small difference in bonding can have such a huge impact on the properties of the material.
Absolutely. And carbon's structural diversity doesn't end there. There's also graphene, which is essentially a single layer of graphite, just one atom thick. It's incredibly strong, even stronger than steel for its weight, and an excellent conductor of electricity, making it incredibly promising for all sorts of applications, from electronics to advanced materials.
It sounds like graphene has the potential to revolutionize a lot of industries.
It really does. And then there are fullerenes, which are molecules made up of carbon atoms arranged in hollow shapes, often spherical or cylindrical. The first fullerene discovered was Buckminster fullerene, which has a spherical shape like a football made up of 60 carbon atoms. These structures also have unique properties and potential applications in nanotechnology and materials science.
Carbon is a real superstar of the periodic table, isn't it? So much variety in bonding and structure, leading to such a wide range of materials.
Absolutely. Now, speaking of tiny structures, let's talk about nanoparticles.
Okay, nanoparticles. These are even smaller than those fullerenes we just talked about, aren't they? What exactly are they?
Nanoparticles are tiny particles, just a few nanometers across. A nanometer is 1/1000th of a meter, so we're talking about clusters of just a few hundred atoms. They're smaller than the wavelengths of visible light, which is why they can't be seen with an ordinary microscope.
Wow, so they're incredibly small. What's so special about being that tiny? How does their size affect their properties?
Well, one of the most significant things is that nanoparticles have an incredibly high surface area to volume ratio. If you imagine taking a large cube and cutting it into smaller and smaller cubes, you create more and more surface area while the total volume stays the same.
Right, so it's like taking that sugar cube and grinding it down into a fine powder. You still have the same amount of sugar, but now it has much more surface area exposed.
Exactly. And this high surface area to volume ratio can have a big impact on how nanoparticles behave. For example, they can be much more reactive than larger particles of the same material because more of their atoms are exposed on the surface and available to interact with other substances.
Okay, so it's not just about what they're made of, it's also about how much of their surface is exposed. What are some of the ways we're actually using nanoparticles these days?
Nanoparticles are being used in a huge variety of applications. They can be used to create incredibly strong and lightweight materials, like carbon nanotubes being added to plastics to make them tougher. They're being used in some sunscreens, where they can absorb ultraviolet light without leaving a white residue on the skin.
Right, so they're already finding their way into everyday products.
Exactly. And the potential applications of nanoparticles are vast. Researchers are exploring their use in medicine, for targeted drug delivery, and even for fighting cancer cells. They're being investigated for use in more efficient solar panels and even in self-cleaning surfaces that repel water and dirt. The possibilities really seem endless.
It's incredible how such tiny particles can have such a big impact. But are there any potential downsides to using nanoparticles?
Well, that's an important question. Because they're so small, there are concerns about how they might interact with living organisms and the environment. If they get into the body, for example, could they cause damage to cells or organs? More research is needed to fully understand the potential risks and how to manage them safely.
It sounds like we need to be cautious and do our homework before we start using nanoparticles everywhere.
Absolutely. It's important to weigh the potential benefits against the potential risks and to ensure that any new nanomaterials are thoroughly tested and regulated before they're widely used. Okay, so we've covered a lot of ground today. From ionic bonds to covalent bonds to metallic bonds, from small molecules to polymers to giant covalent structures, and even down to the incredibly tiny world of nanoparticles.
It's clear that understanding how atoms bond together and the structures they form is absolutely fundamental to understanding the properties of matter. It explains why a diamond is hard and a piece of metal can conduct electricity. It even explains why water boils at a relatively low temperature and why we can mold plastics into all sorts of shapes.
And as we continue to explore and manipulate matter at the atomic and nanoscale levels, who knows what amazing new materials and technologies we'll be able to create.
It's an exciting time to be studying chemistry, that's for sure. Well, that's all we have time for in this deep dive, but hopefully you've come away with a better understanding of the fascinating world of bonding, structure, and the properties of matter.
Absolutely. And next time you pick up a pencil or put on some sunscreen or use your phone, take a moment to think about those tiny atoms and how they're connected. It's all down to the amazing world of chemical bonding.
It really is. Thanks for joining us on the deep dive. See you next time.